Picture a soldier somewhere in Iraq in 2003, the first weeks of the invasion. He is carrying the most advanced service carbine the United States Army has ever issued. It has a collapsible stock, a short barrel, a full auto selector. It is supposed to be the definitive close-quarters weapon for the modern battlefield. And then, it jams. That moment did not happen because of bad luck. It happened because of a chain of engineering compromises, rushed approvals, and institutional inertia that stretched back nearly a decade before that soldier ever set foot in the country. The M4 Carbine did not fail in Iraq because it was a bad weapon. It failed because the people responsible for getting it right had been handed evidence of its problems for years and had chosen repeatedly to move on. This is the story of how that happened. It starts in 1994, before the M4A1 ever went into production, with an accuracy requirement that was physically impossible to meet. The Army wanted the carbine to group shots inside a 4x3.4-inch pattern at 600 yards, firing standard M855 ball ammunition. On paper, that sounds like a reasonable combat standard. In practice, it was asking a 14.5-inch barrel to perform at sub-MOA precision levels, the kind of accuracy you would expect from a precision bolt-action rifle on a bench rest, not from a gas-operated carbine in the hands of an infantry soldier. The best that M855 could deliver from a match-grade barrel at that distance was roughly 2 MOA. A standard production barrel in field conditions produced vertical dispersion somewhere between 12 and 18 inches at 600 yards. The requirement was not achievable. Everyone involved in the testing process knew it, and the Army approved the rifle for production anyway. That decision set the tone for everything that followed. The first serious mechanical failure showed up almost immediately. The original M4A1 barrel was not built to sustain full auto fire. The Army's own 1996 study documented barrel ruptures occurring between 540 and 596 rounds when fired continuously. To put that in context, 3 consecutive magazines on full auto is 90 rounds. The barrel was failing at 6 times that rate before it even reached the point where a soldier would need it most. The barrel walls were losing structural integrity under heat faster than anyone had accounted for. In a sustained firefight where suppressive fire is not a luxury, but a tactical necessity, the M4A1 could not keep up with the role it had been issued for. The fix came from the Navy's Crane Division. Their answer was a heavier barrel profile, more mass to absorb heat before the metal began to deform. Crane set a specific target. The new barrel had to survive at least 800 rounds of sustained full auto before failing. Testing confirmed the heavier profile met that threshold. Problem solved. Except that changing the barrel immediately exposed the next problem. The new heavy barrel came with chrome lining inside the chamber, which was standard practice for durability and corrosion resistance. But the chrome had been applied slightly too thick, or the chamber itself cut slightly too narrow, in some cases both. The difference was a matter of fractions of a millimeter, and it was completely invisible on a cold weapon sitting on an inspection bench. The moment the barrel began to heat up under firing, those tight tolerances tightened further. Brass casings expanded under pressure and then refused to extract cleanly. The extractor could not overcome the friction. Spent cases stuck. The weapon stopped firing. The quality control process had been approving carbines with a built-in failure mode that only activated once the gun reached operating temperature. Nobody knew how many weapons across how many units were carrying the same hidden defect. The Crane Division responded with a new extractor design, a 5-coil spring replacing the original 4-coil, paired with a rubber O-ring wrapped around the extractor body to increase the mechanical grip on each casing. The combination worked. A 15% failure rate effectively disappeared. Army armorers were retrofitting these extractors into carbines bound for Iraq within weeks. There was no time to run the fix under anything resembling actual combat conditions. Every M4A1 that crossed into Iraq during the initial invasion was carrying a component that had been changed specifically because a manufacturing defect had been caught at the last possible moment. While the barrel and extractor problems were being addressed, a more fundamental issue was sitting in plain sight. The M4A1's carbine-length gas system had been running the bolt carrier group harder than necessary from the very beginning of the platform's life. On a 14.5-inch barrel, a carbine-length gas port bleeds propellant gas into the action earlier in the bullet's travel at higher pressure than a mid-length system would. The bolt carrier moves faster. Components wear out sooner. The weapon runs hotter and dirtier. The Army understood the physics well enough to document the problem. Crane's testing would eventually confirm that switching to a mid-length gas system cut the failure rate roughly in half over 30,000 rounds compared to the carbine-length configuration. None of that information prompted any action for nearly 2 decades. The carbine-length rifles were already in mass production. Changing the gas system meant retooling, new parts, new logistics chains, and significant cost. So the data sat in reports, and the overgassing problem remained, quietly accelerating wear on every M4A1 in service. Full auto reliability brought its own separate problem. Slow motion footage of the M4A1 cycling on full auto revealed something the naked eye could not catch. The bolt carrier was moving fast enough that it was beginning to rebound before the next round had fully chambered. The bolt was closing, then bouncing fractionally back open. Then the firing pin was attempting to strike a primer on a cartridge that was not quite fully seated. It did not always result in a catastrophic failure, but it produced light primer strikes and misfires at a rate that degraded full auto reliability in precisely the role the M4A1 had been designed and issued for. The fix was a heavier buffer, the H2, installed in the stock. The additional mass slowed the bolt carrier's rearward travel just enough to keep the bolt fully seated during the cycling sequence. Armorers replaced the buffers and handed the carbines back. Most soldiers never noticed the change. The full auto reliability that the M4A1 had been missing since 1995 was quietly corrected 12 years after the problem had first been identified. By the mid-2000s, with the wars in Iraq and Afghanistan driving intense scrutiny of every piece of infantry equipment, the Army commissioned a formal dust and reliability comparison between the M4 and several competing designs. The results were not flattering. The M4 finished last, 863 stoppages and 19 major failures across 6,000 rounds, while every competing platform handled the same conditions with significantly fewer interruptions. The finding was not that the M4 was uniquely defective. It was that the direct impingement gas system, where propellant gas is routed back into the action to cycle the bolt, tolerates contamination less well than piston-driven alternatives when lubrication breaks down under sustained fire. The report noted that soldiers in the field were maintaining their M4s better than Army doctrine actually required, which was part of why the weapons were still functioning at all. The test data pointed clearly toward a piston-driven replacement. It did not produce one. There was one more mechanical problem that persisted long after it should have been addressed: the 3-round burst mechanism. The burst cam in the standard M4 did not reset between trigger pulls. If a 2-round burst fired and the trigger was released, The next pull would produce only one round before the cam completed its cycle. The breakpoint changed depending on where the cam happened to be sitting after the last shot. In practical terms, this meant soldiers could not develop consistent muscle memory for the weapon on automatic. The trigger behavior was unpredictable from shot to shot. The burst mechanism accomplished nothing useful in terms of ammunition discipline. It simply made the weapon harder to control in the moment when consistency mattered most. When the Army announced M4A1 upgrades in 2010, nearly 5 years into the Afghanistan campaign, some Special Forces operators were already fitting their own ambidextrous selectors from commercially sourced spare parts. The Army had never issued them a carbine with one. In 2012, the M855A1 Enhanced Performance Round entered service. It was a genuine improvement in terminal ballistics, with better penetration through barriers, more reliable performance at longer ranges, and better performance out of shorter barrels. It addressed real deficiencies in the original M855 that had been documented throughout a decade of combat. It also ran at higher chamber pressures than the M4A1 had been designed to handle. Barrel life shortened, and bolt components wore faster. The wear curve that the overgassed carbine-length gas system had been accelerating for years now accelerated further. The gap between what the platform had been built to tolerate and what the current ammunition demanded of it kept widening. At some point in that process, the honest answer was that the M4 had been patched enough. The accumulation of fixes, including a heavier barrel, a new extractor, an H2 buffer, and improved springs, produced a weapon substantially better than what had shipped in the 1990s. But each fix had been a response to a symptom rather than a rethinking of the underlying system. The URGI program, the Mark 18 and M4A1 URGI variants, developed through SOCOM, was the first formal acknowledgement that the carbine length gas system needed to change. The barrel length stayed the same, 14.5 inches. But the gas port moved back to a mid-length position, directly correcting the overpressure problem that had been documented and understood since the platform entered service. The data supporting that switch had existed for years. Crane had confirmed it. The wear numbers had confirmed it. The operational experience of 2 prolonged wars had confirmed it. SOCOM received the upgrade approximately 24 years after the M4A1 first deployed, and 7 years after the M855. A1 had begun compounding the wear problem. The gas system change was designed to fix. The majority of the conventional Army is still waiting. That is not an indictment of the engineers who worked on the M4. Most of the people who identified these problems did exactly what they were supposed to do. They ran the tests, filed the reports, and proposed the solutions. The system that delayed acting on those reports for years, and in some cases for decades, is a different story. When the evidence is on the table, and the decision is to move on, the cost does not disappear. It just gets paid later by someone else, in a place where the consequences are harder to document.